Hey guys, in this video I want to do a little bit of exam review for you guys to basically discuss the main types of reactions that we've discussed through this entire semester. We'll start with the organic type reactions, and then we'll also switch and talk a little bit about the enzymatic type reactions, which are essentially the same, but the nomenclature is sometimes a little different. All right, so we're going to start out with the types of reactions that you might want to think about knowing over here. And I'm going to give some examples. All right, so the first one is a hydrogenation reaction. So in a hydrogenation reaction, okay, what's happening is we're adding hydrogens onto our compound. So here we have, say, an alkene, and that's being hydrogenated to give an alkane. And the classic reagents to do this is H2 and some metal. Okay, like nickel or platinum, something like that. So that's often the reagents. So I'll have another column here, reagents. Okay, now dehydrogenation. If you want to do a dehydrogenation, it's essentially the reverse. We're going to take a simple alkane and we're going to convert it now into a double bond. So in this case, we have to remove two hydrogens. Now, we didn't actually learn a reaction that could do that in the organic part of the semester, but we did learn something in the enzyme part. This was the conversion of FAD to FADH2. We saw a couple reactions where the flavin nucleotide cofactor could actually do this type of reaction. So that's called a dehydrogenation. It's sort of the reverse of hydrogenation. Halogenation. Let's look at what that is. So here if I had, again, an alkene, and let's say we put two chlorines on that. Okay, so notice I've gone from the alkene to this one. It's a halogenation because I've added two halogens across that double bond. And this could have also been bromine, Br2. So the classic reagent are the X2 reagents, where X can be either chlorine or bromine. So that's called a halogenation reaction. The next type is called the halohydrogenation, and that's kind of a mix between these two. Here's what we're going to do for this one. We're going to add a chlorine and a hydrogen. So this is where we're adding HX. Oops, HX. So that's called a halohydrogenation, where we add a halogen to one of the carbons and a hydrogen to the other. In this particular reaction, we'll just put an asterisk next to it. That one, you would need to think about one of the rules we learned back in organic chemistry, Markovnikov's rule, where the X group of an HX reagent is going to add to the more substituted carbon of the double bond. So I guess in this case, if I wanted to make that a little bit truer to form, or a little bit better example, if I had a methyl group here, this would be the more substituted carbon of my double bond, so my halogen would end up adding there. And my hydrogen would add there. So that's called a halohydrogenation. Hydration, as the name would imply, is the addition of water. And there's an H+ catalyst. And this one also is going to follow Markovnikov's rule, where our OH group would add to the more substituted carbon of the double bond, and our hydrogen would add to the least substituted carbon of the double bond. So these two are very similar. Water can be considered like an HX reagent if you rewrite it as HOH, where OH is our X group. So following again Markovnikov's rule, we'll put a star next to that one. The X group, which is from water, is ending up on the more substituted carbon of the double bond. And then lastly, a dehydration reaction. That's going to be essentially the reverse of this one. We're going to now take, let's say, this alcohol, and we're going to dehydrate it. All right? So actually, yeah, we'll just keep that as our example. So in this case, we're going to introduce a double bond here. And we could have also done it over on the other side as well, but essentially we're going to be removing water. And the reagents to do that are just H+ and heat, 180 degrees. So high heat is going to dehydrate an alcohol. So anytime you're stripping out water from some molecule to introduce a double bond, that's called a dehydration reaction. All right, and this particular reaction, we had to use a different rule. This was called Zaitsev's rule. Okay, so that summarizes some of the major reactions, at least in the organic chem part. I'll do some more here on the next section, but definitely go back and get some practice at looking at some of these problems and then identifying. The key here is the type of reaction. You need to have a good grasp of these names and be able to relate them to the type of reaction you see over here. All right, let me go into the next section here. All right, there's a few more of the organic type reactions that I want to definitely review for you here. Next, let's take a neutralization reaction. So when you have an acid or a base and you neutralize it, what's going on with that? So if I had an organic acid, let's say one like this, a carboxylic acid, if I wanted to neutralize it, I would need to use a base, such as sodium hydroxide. Okay, so that base now is going to create the carboxylate salt. Okay, plus water. So in a neutralization reaction, usually water is a byproduct. But if I'm starting with an acid, I need to use a base to do a neutralization reaction. Conversely, if I had, say, an amine, such as this, let's say propylamine, in order to neutralize that amine, I now need to use an acid. So let's use HCl. And what this will do, it will protonate the amine. And I would have chloride as my counter ion, plus, again, water. Again, that's a neutralization reaction. But just be careful when you're looking at these. If you start with an acid, like a carboxylic acid, you're going to need to use base to neutralize it. Conversely, if you start with an organic amine, which is an organic base, you need to use HCl or acid to neutralize it. Okay. Next, let's look at reduction. We talked about this in the context of carbonyl chemistry, like aldehydes and ketones. So let's just say we had an aldehyde, and we want to reduce this. So if you want to reduce an aldehyde, ultimately what it's going to produce is a primary alcohol. Okay, and we learned several different reagents that could do this. One was real simple, just H2 and some metal. Okay, that will reduce the double bond. In the biochemistry section, we did see also you could do this type of reaction with the cofactor NADH. NADH will reduce an aldehyde to an alcohol. Okay, so that's called a reduction. Let's look at an oxidation example. Let's do a secondary alcohol now. If I were to oxidize a secondary alcohol, that's going to give me a ketone. Okay, and the types of reagents that we learned that in organic chemistry that could do that are things like the potassium permanganate, KMNO4, or any of the chromate oxidizers. Those are strong oxidizing agents. But in the biochemistry section, we did see that these could also be performed by also NAD. In this case, it would be NAD plus going to NADH. All right. So that's an example of an oxidation reaction. Again, we're converting an alcohol into a carbonyl. Condensation reactions. We actually saw several different types of those. The two main ones that we discussed were esters, the formation of esters, and then also the formation of an amide. When you bring a carboxylic acid and an alcohol together, that's the example that I'll do here, plus an alcohol. Okay, you get an equilibrium reaction where you now form an ester plus water. Okay, so in a condensation reaction, oftentimes, well, almost always, you're going to be joining two components, and then sometimes is then liberated, in this case, water. So this is definitely a condensation reaction. The amide reaction, the amide formation reaction would be exactly the same. Here, instead, you have an amine, it would join, you'd form water, and instead, here you'd have an amide functional group. Those would both be considered and classified as condensation reactions. Now, hydrolysis reactions are essentially the reverse of this. We're going to add water to to a compound like this to reverse the process. So I've listed the two down here for amides. If I were to do that one first, okay, so if I were to treat this with water, and typically you have to add either acid or base catalyst and heat this up, what this will do is water will now add to the carbonyl to break this thing apart, and we would now get our hydrolysis products, which would be this. We would have acetic acid, and in this case methylamine. Now remember, when under acid conditions, you're going to end up protonating the amine product, and it's going to end up becoming a protonated amine. So that's amide hydrolysis, and it can be done either acid or base catalyzed. Typically, you have to do heat. For ester hydrolysis, I saved this one for last. You can do acid catalyzed hydrolysis, and it will give you these reverse products. But I also want to mention specifically base catalyzed hydrolysis for esters. The reason I'm mentioning that one, so here I have, in the presence of base, the products are going to be my carboxylate plus my alcohol, in this case methanol. When you hydrolyze an ester using base, that actually has a special name. It's called saponification. And we saw that when we were talking about fatty acids in the biochemistry section of the class. So when an ester is hydrolyzed using base, it's generally called a saponification. And specifically, this is often used when you're saponifying triacylglycerides to give rise to the 3 fatty acid chains that come off of that. And that's the process that's used in soap making. All right, so I think that summarizes the major organic type reactions. Again, you're looking at these over here, these names, and you need to be able to identify the type of reaction that's in that. This last section, I want to just cover some of the specialized, more enzymatic type reactions. All right, so in this last section, I want to just cover some of the specialized types of reactions that we encountered when we were talking about various enzymes, especially in some of the metabolic pathways. So first, again, this term dehydrogenation. We saw this in the previous little section here, but dehydrogenation when it comes to enzymes, well, the best example we had was, say, when we took, oops, I'm sorry, we need to put that back on there. Okay, when we took this compound, succinate, and we converted it into fumarate. Okay, so succinate, which has, notice, two hydrogens on each of these carbons in the middle, but when we remove those two, we create fumarate. And in order to do that dehydrogenation, we used FAD going to FADH2. So that's a classic example of a dehydrogenation where 2 hydrogens are removed. Now you could also do a dehydrogenation where 1 hydrogen is removed, and that's typically going to involve the NAD cofactor. Next is a hydration type reaction. We saw a number of these where you're simply going to add water to some double bond. And so I won't even give a specific example. I'll just have R groups here. We're just going to add water. And you get something like that, where the double bond is removed and we're adding water onto that. We saw an example of that in the Krebs cycle. There's also an example in beta oxidation. There's a number of examples of that. Phosphorylation. A whole host of reactions in biochemistry that involve phosphorylation. Usually the phosphate source is going to be ATP. So recall we had glucose with one of its OHs here. If we take ATP going to ADP, let's say we're going to make glucose 6-phosphate. Okay, now we have that phosphate on the 6th position of glucose. All right, and those enzymes, typically that do a phosphorylation involving ATP, those are often called kinase enzymes. Dephosphorylation is the exact opposite, so I'm not even going to draw that one. That's where you go in the reverse direction. Your compound now is losing a phosphate, often giving it up to some other compound. In this case, it would convert ADP back to ATP. An isomerization reaction. This one, you may have missed this one, but if you look at glucose 6-phosphate going to fructose 6-phosphate, that involves an isomerization reaction. So if I draw out the Fischer projection now, of glucose, and I'll just stop right there. Oops, this should be a hydrogen, not an oxygen. Carbon 1, 2, and 3. This is a glucose. If this were to isomerize, okay, what can happen is that the position of the double bond can isomerize from carbon 1 to carbon 2, all right? So this can become carbon 1, 2, and 3. And this would be fructose. Notice how carbon 2 has become a ketone. So that's an isomerization reaction where we've isomerized the bond, essentially the double bond, from position 1 to position 2. Notice this also involved the transfer of a hydrogen from carbon 2 to carbon 1 so that we could have the correct number of bonds here. So that's a classic example of an isomerization reaction, the conversion of glucose 6-phosphate to fructose 6-phosphate. And if you look at the name of the enzyme, it actually has the word isomerase in it. Lastly, decarboxylation reactions. As the name implies, that's going to involve the liberation of CO2. The classic example of that one was the conversion of pyruvate to acetyl-CoA. Okay, and in that process, this carbon comes off as CO2. That's called a decarboxylation. Almost always enzymes that do this, especially if there's a ketone right next door to this, it's called an alpha keto group. This is going to involve the cofactor thymine. So examples of that would be the pyruvate dehydrogenase complex, which does this reaction. Also in fermenting yeast, the enzyme pyruvate decarboxylase will do that exact same reaction. It requires thymine. The reverse reaction, a carboxylation reaction, is going to do the exact reverse. It's going to stick a carbon dioxide onto a molecule. So I won't draw that reaction there. But so I think what this helps to summarize now over the course of the last 3 sort of slides, you can see that there are a number of these types of reactions that you really should review and be able to apply those names to what's going on in an actual reaction, and vice versa too. If you're given a reaction, be able to say what the name is. All right, so please review that for your final, and I wish you guys good luck.